All right, guys, let's see if we can finish it up. 8.7, part B. There might be a part C, so we'll just have to kind of see how it goes. 8.7, part B, we're writing the Maclaurin series, okay? And we did all the notes. Oh my goodness, that other video was long, and that was all like notes. We kind of did one example, but now we're going to do 4 more. So let's talk about the directions. Find a Maclaurin series for the given function, okay, using the definition of the Maclaurin series, which is that summation. I'll write that in a minute. Okay, so that we know. And let's jump down to the bottom. Also find the associated radius of convergence. Okay, so we're going to do those 2 things. I want to talk just briefly. These 2 are in the directions also. So I just want to tell you what that means. Well, first of all, this one's kind of obvious. Assume that f of x has a power series expansion. Okay, so not every single function has a power series expansion. Most do, but just keep in mind that there's not a polynomial, right, a power series expansion for all of them. But they said to go ahead and assume that it does. Okay, then it also says do not show that r sub n of x approaches 0. Okay, well, first of all, this is just good to know. This is another way to write the limit as n approaches infinity of r of x equals 0. So we don't have to show that the limit of r sub x equals 0. Well, what in the world does that mean? Well, if we have this function, f of x, okay, we're going to use part of our Maclaurin series. We're going to use part of it to write out a few terms. So I'm going to do capital M for Maclaurin series. Okay. But remember, in the last video I said, I think it was even on the first page, I said, hey, we used about 4 terms. And so this part is the polynomial. Okay, this part is the polynomial. It's the number of terms that we're going to use, number of terms we are using, okay? But it's really a series, so there's really a whole bunch of other terms. So plus, that's what this is. All the other terms that we're not using. All other terms in series we are not using. Okay, so those are all the other terms in the series we're not using. Now, let's just say this. When we did these 4 terms, we got an answer of 7. Okay, well, what the book is saying is, hey, if all the other terms add up to be 10, then really my answer is 17, right? So I'm really supposed to prove that when I get a 7 here, that the rest of these are approaching 0. So now if I get a 7 here, but all the rest of these are approaching 0, then I can clearly say that, yeah, my 4 terms are giving me the answer. Okay, but if I get a 7 here, but really all the other terms add up to be so much more that it actually affects my overall answer of my f of x, then these 4 terms really aren't accurate. So technically, to kind of prove that these 4 terms, or how many ever we use, is accurate, I'm really supposed to show that the remaining has a limit headed towards 0. Okay, notice our book says do not show, because that can be pretty tricky. Okay, that can get pretty tricky pretty fast. And if our book is even saying, don't worry about it, thank you, right? I know I knock our author a lot, right? But this is one time. And a lot of books do this too, though. But just keep in mind that, and we kind of mentioned it at the beginning, we're only using a few terms. So we're kind of hoping, or we have a good educated guess that those 4 terms, or 5 terms, whatever we use, is accurate. But we cannot forget in the back of our mind that we're really doing a series. So there's still a lot more terms out there. Okay, with that said, so that's what those extra pieces in the directions say. We're going to write the Maclaurin series, and we're going to do the radius of conversion. Okay, so let's go. Convergence, sorry. All right, so we got 4 examples. 4 examples. Here we go. All right, so our first example is f of x. This guy, we're going to write it like this. Okay, because let's do our checklist. How come I'm going to rewrite it like this? We have to find derivatives. Okay, so we got to find the first few derivatives. All right, so let's list here. F of x is equal to 5, 1 minus x to the negative 2. Okay, so now what is the first derivative? Okay, so we need to roll this down. Now, I'm not going to write, especially because we have to come up with some stuff. What I notice here is I'm not going to multiply these out. I'm going to write 5 times negative 2. Okay, so I'm going to roll it down, but I'm not going to multiply it. Roll it down, subtract 1, takes me to negative 3. But, huge but here, do not forget you also, because we have a quantity, we have to take the derivative of what's inside. It's very minor, but because this is minus x, the derivative of what's inside is a negative 1. Okay, and so I'm going to rewrite this. Isn't this nice? This is negative 2 and negative 1, so I'm going to write this as 5 times 2. 1 minus x to the negative 3. Okay. All right, so now let's do the second derivative. Okay, we're going to roll it down. So I've got 5 times 2 times a negative 3. Roll it down, subtract 1. But because this is a quantity, I have to take it times the derivative of the quantity. So the derivative is negative 1. So I'm going to rewrite it because these two negatives then cancel each other out. So I've got 5 times 2 times 3. And then 1 minus x to the negative 4. Okay. The third derivative, roll it down. You kind of see a pattern, and that's the goal. The quicker you can see the pattern, you're in good shape. Let's write this one, though. I think I stop here. Maybe we'll do one more. Roll it down, 2 times 3 times negative 4. Subtract 1 from the exponent, but take the derivative of what's inside because it's a quantity. And we get to knock those two out. So 2 times 3 times 4, 1x to the negative 5. Okay. All right, if we do one more, f, the fourth derivative, I think that'll be plenty. Roll it down, so 5, but then I have 2 times 3 times 4, technically to the negative 5. 1 minus x to now the negative 6. But I had to take it times the derivative of the quantity, which then takes these two to positive. Okay, so the very first step, I'm writing these down, the very first step is to find the first few derivatives. Okay, done. We've got more than enough. Now we're going to evaluate each derivative at a, and a is 0. Okay, so we're going to evaluate each of these when x is 0. Okay, so f of 0. I don't think I'm going to write it out. I think on the sign I did. So I'm just going to take a 0, plug it in here. Okay, what happens when I plug a 0 in there? Well, I get 1 minus 0, which is 1. 1 to the negative 2 is still 1. So then I just have 5. Okay, maybe I'll draw a line here because we want to kind of keep those separate. Okay. All right, the first derivative, what happens when I plug in a 0? Okay, I'm actually going to go down here, right? I'm going to use this line. When I plug in a 0, 1 minus 0 is 1. 1 to the negative 3 is still 1. And so I have 5 times 2. Okay, let me write it. I'm going to write it all the way down here because this is the better line. This is a good line. Okay, it doesn't really matter. Space. This is second derivative. All right, I plug in a 0, find your best line here. This is the nice one all simplified. I plug in a 0, I get 1 minus 0, which is 1, to the negative 4th power is still 1. So I really have 5 times 2 times 3. Okay. All right, we're on our way. The third derivative evaluated at 0. Oops, I should have went down to this line, right? I plug in a 0, I get 1. 1 to the negative 5th is still 1. So I really have 5 times 2 times 3 times 4. And then last time, go down here. This is a better one. The fourth derivative, put in a 0. Same thing, right? That's kind of nice. That gets repeated. So I've got 5, and then I got 2 times 3 times 4 times 5. What is this? Don't worry about the first 5. Don't worry about that first number 5. But what is this, guys? 5 times 4 times 3 times 2 times 1, if I need it. This is 5 factorial. 4 times 3 times 2 times 1, this is 4 factorial. 3 times 2 times 1 technically is 3 factorial. 2 times 1 is 2 factorial. Okay, and this would be 1 factorial. Right? I could add a 1 factorial if I wanted. Okay, so now, so evaluate each. We did that. Write out the terms using the values from step 2 using this guy. So let's rewrite it. We're using n equals 0 to infinity. F of n, we plugged in 0, and then it's n factorial x to the n. Okay. All right. So when I do 0, okay, that's f of 0, or that is the original function. Okay, I got this guy. I got 5, if I need it, 1 factorial, right? And then over 0 factorial, x to the 0. Okay, wherever there's an n, I'm plugging in a 0. Okay, now plus, I'm going to plug in a 1. So f with a 1, there's the first derivative evaluated at 0. So I go to my first derivative evaluated at 0. I've got 5, and then I've got times 2 factorial. And then these n's are just becoming 1, right? What did I plug in? I forgot what I plugged in. 1 factorial, x to the first. Okay. All right, now we plugged in. Don't forget you start with a 0. So you plug in a 0, you plug in a 1. Now I'm going to plug in a 2. When I plug in a 2, it's really asking for the second derivative evaluated at 0. Second derivative evaluated at 0, 5. And then I'm going to change that other to 3 factorial over n, which was 2 factorial, and then x squared. Okay. All right, now when we plug in a 3, it's asking for the third derivative evaluated at 0. So here's my third derivative evaluated at 0. So I got 5 times 4 factorial over, and that's really only 3 factorial, x to the third. All right, and let's do, since we have it, let's do the last one. We're plugging in 0, 1, 2, 3. Let's plug in a 4. So the fourth derivative, that's this guy. Can we see? Yeah, we can see. Okay, so 5. And then notice these here are the 5 factorial, right, over 4 factorial, and then x to the 4th. Okay, so now notice this is nice. Nothing canceled out. Nothing canceled out. So now from this, n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. Now I just have to kind of rewrite it. Most of it is going to stay the same. I kind of basically have to come up a pattern for this, because these are going to match, right? N equals 0 to infinity. My n is 0. This is 0, 1, 2, 3, 4. Usually I kind of swing backwards. So this matches nicely. So this is going to stay n factorial, which, you know, if stuff doesn't cancel out, that's usually the case. And same thing here. These numbers match exactly, right? 1, 1, 2, 2. So that's going to stay x to the n. Okay. So now I need a pattern. They all have a 5. Every single one of them has that beginning 5. Okay. Now, when it's 0, it's 1 factorial. When it's 1, it's 2 factorial. When it's 2, it's 3 factorial. So this is n plus 1 factorial. Okay. Not a bad answer. Not a bad answer. But we can, let me rewrite it. Do we have enough room? Yeah. Let me rewrite this. 5 n plus 1 factorial over n factorial x to the n. Okay, that's a pretty good answer. That's not bad. But this, let me see if I have a different color. This, we can simplify this. Remember, like n factorial, and I'm just doing an example. This would be like 5 times 4 times 3 times 2 times 1. This is n plus 1. So if this started with a 5, this starts with a 6. Times 5 times 4 times 3 times 2. We've talked about this before, but I just want to make sure. So all of these cancel except for this last number. So we can actually cancel these. Our best answer here, and I think we can sneak it out. Let me move it up. Okay, we can cancel this. So our best answer is n0 to infinity. The 5 is not going anywhere. All of these on the bottom are going to cancel. And so we literally just have n plus 1 and then x to the n. So even though the pattern started out with that, we were still able to simplify it once we saw this top pattern. Once we get this pattern, we can sometimes still do some canceling. Okay, and so that is it. Let's say I want this when x is 3. Oh, that would be helpful. Instead of doing that, and I realize that this is pretty straightforward, but if for some reason, instead of doing that, I could plug in a 0. I could plug in a 1. I could plug in a 2, and then plug in, I forgot what I said here. Whatever I wanted to evaluate it here was a 3. Then I could plug a 3 in there and get the same answer. Okay, just like we did with sine. Okay, so this and this series, depending, barely fits, depending how many, if I want to write out 3 or 4, maybe 4 or 5 terms, depending what I want to plug in for x here and here, I should get the exact same answer. Okay, all right, now we got to do radius of conversion. Convergence. Why can't I say that? Oh, I'm glad this is the last section. All right, so let me rewrite this. What did we have here? N equals the radius of convergence. So I'm just copying this down. N plus 1 x sub n. Okay. So now we got to do the ratio test. Ratio test. This is kind of nice because we don't have fractions, so it's going to go a little bit quicker, right? Limit as n approaches infinity. We have to put in n plus 1, though. So 5, and then just be careful here, n plus 1, and then I have the plus 1, and then x to the n plus 1, divided by, and then I divide by this guy, x to the n. Okay. Oh, let's see, what else could we do? Let's clean this up a little, clean up and cancel, right? So this is 5, this is n plus 2, and then x to the n, x to the first, over, and then this guy stays. All right, so these guys cancel, and these cancel. All right, so let's take a look. We got the limit as n approaches infinity, absolute value of n, which is important, right? N plus 2, and then we've got the x, and then over n plus 1. Okay. All right, so now, what's the limit as n approaches infinity? If we just are looking at this guy, okay, if we're just looking at that, my exponents are the same. So the limit on the n's is 1. So I have 1 there, but I still have this x. So I have the absolute value of x less than 1. Okay. So negative 1 less than x, which is less than 1. I'm centered at 0, and I'm going from 1 to negative 1. So what is my radius? So really, it's only going to work. It's only going to work when I choose x values between negative 1 and 1. Okay, this only converges when I choose x values between negative 1 and 1. So if I want to evaluate this, it's got to be when an x is between negative 1 and 1. Okay, so definitely a little bit more, but I could always change that by going to a Taylor series. Okay, which most of the time you have to anyways if you're not around 0. Okay, but that's it. We've got our series written, and we know the radius of convergence. Okay. All right, let's try another one. Piece of cake, right, guys? Okay, how are we doing on time? Okay, let's do another one. my last video was long and it was not good to download. So let's see, let's try one more though. F of x equals e to the negative 4x. Okay. All right. So, how are we going to write a Maclaurin series? First few derivatives, then evaluate those derivatives at 0. So let's get our first few. First, we're going to do f of x, e to the negative 4x. Okay. Then we want to take the first derivative. Okay. Now, the derivative of e to the u is e to the u times the derivative of u. We're back to chain rule. So it's going to be e to the negative 4x, but then times the derivative of this guy, which is negative 4. Okay. All right, second derivative. Let's just leave that this way. So it's going to be, remember the constant just sticks around. So the derivative of e to the negative 4x is e to the negative 4x. This guy sticks around, and I still have to do the derivative of this guy, which is negative 4. Okay. All right, so we've got the third derivative. Same thing. This is just a constant. I'm just choosing not to multiply it out. So my derivative of this guy is e to the negative 4x times the derivative of this, which is negative 4, and then my constant or constants just hang around. Okay, let's do one more. Derivative of this guy is e to the negative 4x times negative 4, and then my constants just hang around. Okay. Remember, do not forget, if I have x plus 4, this derivative goes to 0. But what happens if I have 4x? If I'm multiplying, this number stays. That number stays, right? And this, it just affects this, which goes to 1, but the 4 stays. So my coefficient stays, right? Think if I have 4x squared, I roll it down. Now, normally I change it to 8, but otherwise I could write 4 times 2 and then the x part. Okay, so coefficients stay. If I'm multiplying, it stays. If I'm adding or subtracting, yeah, then it goes away. Okay, all right. All right, so those guys stay. Okay, so now we're going to evaluate at 0. We're going to evaluate at 0. So when I plug in a 0, I get 0. I get e to the 0, which is 1. Okay. All right, same thing here. So now I'm going to evaluate the first derivative at 0. When I plug in a 0, I get e to the 0, which is 1. So I really have negative 4. Okay. Here I put same thing. Okay, so second derivative, you kind of maybe already even see the pattern. I plug in a 0, and I get e to the 0, which is 1. So I got negative 4 times negative 4. So I'm going to rewrite this. I'm going to go ahead and change the negative. So I'm going to write it as 4 times 4. Okay. All right. Third derivative, evaluated at 0. Same thing, right? I plug in a 0. The exponent goes to 0. E to the 0 is 1. So I'm going to clean this up a little, right? Negative times a negative times a negative is a negative. And then I've got the 3 4s. Okay, let's do it one more time. Plug in a 0. E to the 0 is 1. So I've got these 4 4s. Negative times a negative times a negative times a negative is a positive. So I really just have the 4s. Okay. All right. Can we see this is 4 to the 4th? This is, now it's negative, and then 4 to the 3rd. This guy is positive 4 squared. This is negative 4 to the 1st, right? And we could even think of this as a 4 to the 0 if we needed it, okay? Or we could think of it like that. Okay, so now look it up. What is it? It's the summation from 0 to theta, or theta, what am I saying? 0 to infinity, oh my goodness. F of n evaluated at 0, and then it's n factorial x to the n. Okay, all right. So We plug in a 0. Let's do it over here. I like to work backwards. We plug in a 0, we get 0 factorial, x to the 0. Now we want the function, the original function, because we're plugging in a 0 here, the original function evaluated at 0. Okay, it's up to you. We can write it either way. And maybe we'll write it like this. Okay, if we need to change it, we can. All right, we plug in a 1. So we've got 1 factorial, x to the first. All right, we plug in a 1, so we're asking for the derivative, the first derivative evaluated at 0. First derivative evaluated at 0, negative 4 to the first. Okay. All right, then we plug in a 2. 2 factorial, x squared. Now we want a 2 there. I'm supposed to say n. Oh, my goodness. So we plug in a 2 there. So the second derivative evaluated at 0 is 4. Yeah, evaluated with the 0 in there is 4 squared. Okay, plug in a 3. We get the idea. Look at the third derivative evaluated at 0. Third derivative is going to be negative 4 to the third. Okay, and then if we don't see the pattern yet, 4 factorial, x to the fourth. Now remember, technically this keeps going on. Okay, and then it's going to be positive. We're going to evaluate it, the fourth derivative evaluated at 0, 4 to the fourth. Okay, so we can write this if we want. This is n equals 0. This is n equals 1. I don't think anything goes away here. So let's rewrite it and then see if anything cancels. Okay, so we got the summation, n equals 0 to infinity. Let's work backwards. These numbers match beautifully. So at least right now, it's going to be n factorial. It might simplify later, but that's perfect. These numbers match. Okay, so that's going to be x to the n. Okay, so now, and this actually matches. That's not bad. So this is going to be 4 to the n. All those numbers match. Look, 1, 1, 1, 2, 2, 2, 3. So all those match. So the only other thing we have to take into consideration is every other one alternates. If the exponent is odd, then it's negative. So we're going to do negative 1 to the n. Okay. So when n is 1, it's going to stay negative. When n is 2, then this will actually be positive. When n is 3, it'll give me the negative that I need. When n is 4, it's even, so it goes to positive. Great. I don't think in this problem anything cancels. Maybe we should have done this one first. So yeah, that's it. If we just let's just leave it. We can maybe extend that out. That's it. Okay, so now let's see what x values does this hold true. So I don't even need to, we're going to go with that. All right, so let's look at, so that's that guy. Let's look at our radius of convergence. Okay, let's move that up. Let me rewrite it, so I'm at the top of the page. All right, so let's rewrite this. Radius of convergence. Let's rewrite that. And I'll put the x to the n on the top then. Sometimes that's just easier. And then n factorial. Okay, so now radius of convergence. We're going to use the ratio test. Ratio test. The limit as n approaches infinity of plug in your n plus 1 over n plus 1. Okay, and then divided by, now let's just do it, divided by, and then the n. And then remember, what do we do instead of dividing? Multiply. We don't know. Okay, let's slide this up. Multiply by the reciprocal. So the limit as n approaches infinity. This stays, but let's change it, right? Let's change it to n, negative 1 to the first, 4 to the n, 4 to the first, x to the n, x to the first. Okay, and then the bottom will pretty much stay. And then we're going to take it times the reciprocal of this guy. Okay, negative 1 to the n, 4 to the n, x to the n. Okay, good. Okay, so big, but let's see what cancels. These guys cancel. The 4 to the n cancels. X to the n cancels. Negative 1, because we're doing all multiplication, we're doing absolute value, so I'm going to write ABS, and so that kind of goes away, right? Because the absolute value of negative 1 is 1. So I have a 4, and I have this x. Now let's talk about n factorial and n plus 1 factorial. What is left? The only thing left is the n plus 1, that very last term. Everything else is going to cancel with this term. Okay, the limit now as n approaches infinity. Well, as n gets bigger and bigger, this limit is 0. Okay, so this guy is 0. The x is not part of it because I'm doing that as n approaches 0. So I have the limit, I have 0, right? But then I still have the absolute value of x. So that limit is 0. I still have the absolute value of x. Ratio test says it's when it's less than 0. Okay, you give me an x value, it's going to go to 0. It's always going to be less than 1. Give me an x value 100, I take it times 0, it's 0, that's going to be less than 1. So my radius of convergence is any number that you choose. Okay. All right, let's stop there just for video's sake, and then we got 2 more examples.